Welcome to The Explainer. Today, we're diving into a cosmic mystery that is literally breaking our understanding of how planets evolve, the anomaly of Ganymede's heart. Recent research from the journal Science Advances suggests that the core of Jupiter's massive moon, which is actually the largest moon in our entire solar system, might still be forming right now, and that completely defies everything we thought we knew about how worlds age.
So what exactly is hiding inside Jupiter's largest moon? Well, to really appreciate this mystery, we've got to travel back to 1996. When NASA's Galileo spacecraft was out there taking readings in the dark depths of our solar system, it made a truly shocking discovery about Ganymede. It detected a magnetic field. Now, a magnetic field means Ganymede isn't just some cold, dead rock floating in space. It's active. There's something dynamic happening deep within its interior. It essentially has a beating heart. And scientists have been trying to figure out exactly what that heart looks like for almost 3 decades now.
The sheer contrast between Ganymede and its peers is just staggering. Ganymede, internally powered magnetic dynamo. Every other known moon, no internal magnetic field. Literally none. Ganymede stands completely alone here. You see, an internally powered magnetic field is a really specific trait. It's usually strictly reserved for full-fledged planets like Earth, Mercury, and the massive gas giants. For Ganymede to have one, it means it's playing by planetary rules, not moon rules.
The engine, generating a magnetic field. To understand why Ganymede is playing by its own rules, we first need to look at its engine. A magnetic field doesn't just spontaneously exist out of nowhere, right? It requires a massive, active, internal power source to generate it and, crucially, to sustain it over billions of years. Let's talk about a magnetic dynamo, a mechanism where the continuous convective motion of electrically conducting liquid generates and sustains a magnetic field. To ground this concept, we just have to look right beneath our feet. Earth's magnetic field, the one that protects our atmosphere and makes our compass needles point north, arises from the motions of liquid metal in our outer core, swirling around a solid iron inner core. It's this churning, swirling engine. To possess a magnetic field, Ganymede must have a very similar liquid engine churning away deep inside.
Researchers are proposing a truly fascinating mechanism called iron snow to explain how Ganymede's engine operates. Step 1. Liquid metal cools and crystallizes near the top. Step 2. Dense iron sinks and remelts deep down. Step 3. The resultant convective motion generates electrical currents. Basically, near the top of the moon's core, liquid iron cools and actually crystallizes into solid particles. These solid, dense iron particles, the snow, sink downward, eventually remelting as they reach deeper, much hotter layers. This continuous falling and melting drives a massive convective motion. It's exactly like a giant planetary lava lamp. That constant rise and fall of material is what keeps the magnetic dynamo alive and kicking.
But here's the complication, the cold start problem. That lava lamp model relies on one major assumption. It assumes Ganymede formed relatively hot enough that its metals could easily separate and build a core very early in the moon's history. But newer models suggest icy moons like Ganymede actually formed far too cold for that kind of rapid separation. If it started out freezing cold, how on Earth, or, well, how on Ganymede, did it ever get hot enough to create an iron core and kickstart this magnetic dynamo?
To solve this puzzle, a team led by Caltech planetary scientist Kevin Tren modeled Ganymede's internal heat over time. 4.5 billion years ago, a cold, undifferentiated start. Rocks and ice were just all mixed together. Fast forward to about 2 billion years ago, radioactive and tidal heating slowly melts water and iron. The slow process of radioactive decay, combined with intense tidal squeezing from Jupiter's massive gravity, gradually warmed the moon up. This incredibly slow heating released water from the rocks, creating Ganymede's vast subsurface ocean. Concurrently, iron-rich melt began to separate and trickle down. And that brings us to the present day. Iron trickles down, and the core is still forming. Because it took so long to heat up, that iron is still trickling down right now.
Which brings us to an ongoing iron snowstorm. This is the big twist, guys. We aren't just looking at the ancient history of a moon. We are witnessing an ongoing iron snowstorm. Tren's simulations showed that this slow, steady drip of dense metal doesn't just build a core over time. The very act of the iron dropping down actively stirs that liquid interior. It's the falling of this fresh iron today, right now, that is driving the motion and sustaining that magnetic dynamo.
This crucial point is captured perfectly by Kevin Tren himself. I'm used to thinking of core formation being this ancient process, and he's spot on, right? When we look at planets like Earth or Mars, their cores finished forming billions of years ago. Core formation is almost universally considered the opening chapter of a planetary body's life.
But this new work suggests that for a cold start icy moon like Ganymede, this foundational process was delayed by billions of years. That makes it the only known world in our entire solar system where a metallic core is actively being built today. Mind-blowing.
Of course, science is a rigorous process, and not everyone is ready to just rewrite the textbooks quite yet. Doris Brewer, a planetary scientist at the German Aerospace Center, notes, "In principle, the story sounds interesting and reasonable, but I'm not totally convinced that they considered all the effects." And, she has a really fair point. For this ongoing iron snowstorm theory to be true, Ganymede must have threaded an impossibly narrow thermal path. If it heated up too slowly, the iron would have never melted. But if it heated up too quickly, the core would have finished forming eons ago, and the dynamo would have shut down. It is a delicate cosmic balancing act with a ton of variables at play.
So, we are left with the ultimate sting operation. We have a groundbreaking theory, and we have completely reasonable scientific skepticism. So how do we solve the case? Well, planetary geophysicist James Roberts points out that we're actually setting up a deep space sting operation right now to look inside Ganymede and find out the truth once and for all.
The magic number here is 2031. That is when the European Space Agency's Jupiter Icy Moons Explorer, which is brilliantly acronymed as the JUICE spacecraft, by the way, is scheduled to finally arrive at Ganymede. We literally have a spacecraft already on its way to solve this exact mystery.
How exactly will JUICE act as our cosmic detective? Well, first, it's going to measure the gravity field to find the deep mass distribution. This will definitively answer if the dense iron is already fully concentrated into a compact, finished core or if it's still mixed throughout the interior, which would prove the ongoing iron snowstorm theory. Then, it'll refine core size estimates using magnetic data. The spacecraft is absolutely tailor-made to peer right through Ganymede's icy shell.
Which leaves us with a massive question. Is Ganymede the only world still building its heart? Even right now, without JUICE's final confirmation, Ganymede's magnetic field puts it in a class entirely of its own. But if the data in 2031 confirms Kevin Trin's models, Ganymede becomes the single known place in our solar system actively constructing its core today. It really forces us to wonder what other delayed ancient processes might be ticking away right now in the dark, icy corners of our universe. Thanks so much for joining this explainer. We'll see you next time.